Welcome to Science and Physics. Today we are diving into one of the most intriguing and mind-bending realms of science, quantum mechanics. Get ready to explore the very foundations of our universe, where particles can be waves and reality is stranger than fiction. Stay with us to uncover the basics of quantum mechanics and how it challenges our understanding of the natural world. Our journey begins in the early 20th century, a time when classical physics reigned supreme. The world seemed predictable, governed by Newton's laws of motion and Maxwell's equations of electromagnetism. But as scientists delved deeper into the behavior of light and matter, they discovered phenomena that couldn't be explained by classical theories. It all started with Max Planck in 1900. While studying black-body radiation, Planck proposed that energy is not continuous but comes in discrete packets called quanta. This radical idea laid the groundwork for quantum theory. Soon after, Albert Einstein explained the photoelectric effect by suggesting that light itself is made of quanta, or photons. But the real game changer came in the 1920s. Scientists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger developed a new framework to describe atomic and subatomic processes, quantum mechanics. One of the most perplexing aspects of this theory is wave-particle duality. Simply put, particles such as electrons can exhibit both particle-like and wave-like behavior, depending on how we observe them. To understand wave-particle duality, let's explore the famous double-slit experiment. Imagine firing electrons at a barrier with two slits. If we observe which slit the electrons pass through, they behave like particles, creating two distinct bands on a screen behind the slits. But if we don't observe the path, the electrons behave like waves, producing an interference pattern of multiple bands. This experiment reveals the dual nature of particles, showing that observation itself plays a critical role in determining behavior. This leads us to Werner Heisenberg's uncertainty principle, a cornerstone of quantum mechanics. It states that we cannot simultaneously know both the exact position and momentum of a particle. The more precisely we know one, the less precisely we know the other. This inherent uncertainty challenges the deterministic view of the universe that classical physics provided. Now, let's delve into one of the most famous thought experiments in quantum mechanics, Schrödinger's cat. Imagine a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, killing the cat. Quantum mechanics suggests that until we open the box and observe, the cat is simultaneously alive and dead, a superposition of states. At the heart of quantum mechanics is the wave function, a mathematical description of the quantum state of a system. When we measure a quantum system, the wave function collapses to a single outcome, breaking the superposition. This collapse is still a topic of debate and interpretation among physicists. One interpretation, the Copenhagen interpretation, posits that the act of measurement causes this collapse, while other interpretations suggest different mechanisms. Another mind-bending phenomenon is quantum entanglement. When two particles become entangled, their properties are linked, no matter the distance between them. Measuring one particle instantly affects the state of the other, a concept that even Einstein called spooky action at a distance. This challenges our understanding of locality and causality in the universe. Experiments have confirmed entanglement, making it a cornerstone of quantum mechanics and a foundation for emerging technologies like quantum computing and quantum cryptography. Despite its abstract nature, quantum mechanics has profound real-world applications. It underpins much of modern technology, from semiconductors and transistors in computer chips to MRI machines in medical imaging. Quantum mechanics also plays a crucial role in understanding chemical reactions and developing new materials. For example, the principles of quantum mechanics are essential in designing pharmaceuticals and optimizing industrial processes. Looking ahead, quantum mechanics is driving the next technological revolution, quantum computing. Quantum computers harness the principles of superposition and entanglement to perform calculations far beyond the capability of classical computers. They hold the promise of solving complex problems in cryptography, material science, and artificial intelligence. Major tech companies and research institutions are racing to develop practical quantum computers, which could revolutionize industries and lead to breakthroughs we can't yet imagine. But even as we harness its power, the true nature of quantum mechanics remains a mystery. Various interpretations attempt to explain its peculiarities, from the Copenhagen interpretation to the many worlds hypothesis, which suggests that every quantum event spawns a parallel universe. Another intriguing interpretation is the pilot wave theory, which reintroduces determinism to quantum mechanics. The quest to fully understand quantum mechanics continues to inspire and challenge physicists worldwide. In conclusion, quantum mechanics reveals a universe that is far stranger and more fascinating than we ever imagined. It challenges our perceptions of reality, determinism, and the very fabric of the cosmos. As we continue to explore and unravel its mysteries, we invite you to join us on this extraordinary journey. Don't forget to like, subscribe, and hit the notification bell to stay updated with our latest videos on cutting-edge scientific topics.